So in this lesson, guys, we are going to continue with polynomials, but we are going to look at how we are going to add. So today, again, we are just looking at adding, not subtracting. However, guys, again, as a reminder, and I said this earlier, adding a value, okay, or adding a positive value can be written as subtraction. So let's add -5. Well, that's the same thing as subtracting 5. So we will use that with our algebra tiles as we continue along. So again, if you have not gotten algebra tiles from the sub, make sure that you finished the table on the previous page so you can get your algebra tiles. So this is a standard of algebra that you are able to understand the use of algebra tiles to add polynomials. But we also will then use them to just solve algebraically. Algebraically simply means on paper, okay? Just using without using manipulatives. So this is bringing back the solar panel from our last lesson. And again, it says, notice that there are 4 squared or 16 cells. And again, this is how we counted our solar panels in the first place. Each column of 4 has 4 cells. So again, referencing our previous lesson, if a square solar panel with unknown number of cells along the edge can be represented by x squared, how many cells will be in one column of the panel? So again, this is going back to question 2 from the previous lesson. But if it's a square, the one thing I know about a square is that it has the same length and the same width. So if the number of cells can be represented by x squared, that means the length is x, the width is x. So there would be x number of cells in one column. So now you can take out the algebra tiles that should be in the bag given to you by the sub. And if you would, pull out the large blue and red square. So the large blue and red square represents a square that is x by x length. So the large square represents x squared, or a square that is of length x by x. A column of x cells can be represented using this tall, skinny rectangle. And again, that is green on one side and red on the other. And again, this represents x because it has a length of x, like the large square before it, but it has a width of 1. Or again, x times 1 just represents x. And then you have the yellow or cream-colored small squares that represent constant terms, or 1 by 1. So again, the short side on these algebra tiles represents a 1, and the long side on the algebra tiles represents an x. So we have the large blue square is x squared, the skinny rectangle is x, and the small square is a 1. So let's suppose that there are 3 solar panels, each had x number of columns and x rows, 2 columns with x cells, and 3 single solar cells. Lots of words. So we could represent these using algebra tiles. And I know it's written here in your book, guys, but I want you just to have the physical representation in front of you. So find your squares to help set this up in front of you. So we should have 3 blue squares, 2 green rectangles, and 1, 2, 3 small squares. And yes, they should be on the blue, green, and yellow sides. There should not be any red. On your table, there should also be a bucket of colored pencils. There are 2 of each color, so if there are more than 2 people at your group, you will have to do your best to share. Now, First, use your algebra tiles on your desk to represent the polynomial below. So our question is to represent 2x squared minus 3x plus 2. Now, one thing I want you to pay attention to, minus 3x. On your algebra tiles, you'll notice that on each one of them, one side is red. This is a side that represents a negative. So to represent this polynomial, it asks for 2x squared. So we should have 2 blue squares, negative 3x. So we are still using the long rectangles, however, they should be placed on the red side facing up, with our plus 2 at the very end. So again, take a moment to use your algebra tiles and colored pencils available to you at your desk to draw the representation. You could go ahead and pause the video at this time. So if we turn to the next page, again, it's going to show us what we can use algebra tiles for. In the previous problem, we used it to simply model the polynomial. We can use it to identify and remove 0 pairs, and we can use it to write a new polynomial. Now, 0 pairs is where we will get into subtraction here in a bit. Now, example A, which is shown here, is a very good representation of how we're going to use this for addition. So it says add 3x squared minus 3x minus 5 plus 2x squared plus 5x plus 3. Now, one thing I want you to take note of is that both of these polynomials are written inside parentheses. This is very important as we move into subtraction, because if we were to subtract the polynomials, again, the subtraction or the negative would have to be distributed throughout, and it would change the sign of each term. But again, since we are adding, the parentheses don't mean as much, okay? So I know in your pack of algebra tiles, you do not have enough to model this, so please follow along here on the screen. When we model these polynomials, we have 3x squared minus 3x minus 5. So when we start out this model, we should have 3 blue squares, 3 red triangles, 3 rectangles, and then even our constant terms are going to be red because they are being subtracted. You could follow along and model this in your book by using the colored pencils if you would like. That would be a better way since we do not have all of the algebra squares available. For the second polynomial, it's positive 2x squared, and we have positive 5x and a positive 3. So again, if you use color in your book, it would be a lot easier to see what is about to happen. Now, step 2 says identify and remove 0 pairs. Now, 0 pairs, as you can see, have been moved to the very end. A 0 pair simply means that we can remove x squared and an x. Because if we think about it, what is x minus x? Well, it's 0. X minus x is 0. And x minus x is 0. So a 0 pair is simply finding in your algebra tiles a red rectangle that matches with a green rectangle. And if you have a pair of red and green, you can take that away because it will equal 0. And the same thing is true then with our constant terms. 1 minus 1 is 0. So when we remove all the pairs, what we are left with is going to be 5 positive x squares. Because none of them canceled, we had no negative x squares. We are going to have 2 positive x, which are left over from our second polynomial. And we will be left with 2 negative constant terms. We can end with negative numbers. That is fine. What we should not end with is a 0 pair, something that will cancel. So our final answer for this would be 5x squared plus 2x minus 2. Again, take a moment to make sure that you have either outlined these, crossed out your x pairs or your 0 pairs, and take a moment to read over and make sure you understand before moving on. At the bottom of the page here, it says add using algebra tiles. So at this point, the only problem that does not have enough algebra tiles would be letter B. So do your best to combine like terms with letter B. We'll actually look at this one together. One thing that's also different about letter B is that it uses y. This does not matter when it comes to algebra tiles. It can be x, y, z, p, q, r, whatever variable, but if it's squared, it's going to be the large square. If it is just x or y, it's going to be our rectangle, and constants will always be the small cubes. So for this problem, I'm going to go ahead and combine like terms first, or I'll identify like terms. So using a blue color here, I'll identify that I have 2 y squares, or I would have 2 blue squares, and I have positive 3 y squared. In total, that's going to leave me with a positive 5y squared. So my large blue squares are finished. I'm going to move on to green, and it shows me that I have 3y. Well, in the second polynomial, there are no other y values, so that would then leave me with just simply a positive 3y. And then my final constant terms have a positive 6 minus 4, or a negative 4. And if we were looking at this with our algebra tiles, which you could do as well, this would leave me with 1, 2, 3, 4, 5, 6 cream or yellow squares. But right next to that, 1, 2, 3, 4 red. And again, this is a 0 pair. The positive and negatives will cancel, leaving me with positive 2. So again, this is another way that we could look at this. If we do not have algebra tiles, we could use colored pencils or even circles and squares to figure out what our like terms are. So again, at this point, pause the video, take a few minutes to fill out the example problems, and call the sub over to check your work before moving on. after the sub has checked your work, again, we're going to go to the next page. This is page 361. And question 3 asks, can you use algebra tiles to add 4x to the 4th power plus 3x squared plus 15 plus x to the 4th power plus 10x cubed minus 4x squared plus 22x minus 23? If so, model the polynomials and add. If not, explain why. Well, let's for a second look at the values that we're given here. Well, we know we have an algebra tile for our constant values. So we can draw, for this one, we would have a red square, and for 15 we would have a cream or a yellow colored square. We also know that we have tiles for x, 22 long rectangles, and we also have ones for x squared. So we should be fine in this regard. So what we're left to look at in the question that's asking is, can we have algebra tiles to represent 4 to x to the 4th power and x cubed? Well, let's think about it. Again, our models have been of area. X times x gives me x squared. 1 times x gives me x, and then we have 1 times 1 gives me 1. There are no numbers that would multiply by an area to give me x cubed. Or, because I know some of you are thinking this, well, what about x squared times x? Well, in that case, what we would be looking for would be a cube. X cubed, right? Gives us a cube. That, by definition, is not an algebra tile. Okay, it has, yes, length of x, width of x, and a height of x. Gives me x cubed. We don't have cubes. We're looking at algebra tiles, two-dimensional figures. X to the 4th power then raises even a further question. We're looking at a 4th dimension. That definitely cannot be represented by an algebra tile. So can we model this? No, we can't, because we do not have 3-dimensional representation of x cubed, and we have 0 representation possible for x to the 4th power. So using algebra tiles is only ever going to pertain to x squared, x, and 1, or constant terms. Below here, we're going to now look at another vocabulary term, like terms. This is something that we have used throughout the year and in pre-algebra as well. So I have full confidence that we understand what these are. So letter A, are they like terms? No. The exponents are different. They're not the same. B, no. 1 has a variable. If they are like terms, the exponents must be the same and the variables must be the same. So let's look at C. Are the variables the same? Yes. Are the exponents the same? Yes. 1 is a negative and 1 is a positive, but we're not worried about the coefficients. The variable and exponent are the same. This is what we're looking for when we're asked, is it a like term or not? Is the variable and the exponent the same? For part D, we have to be very careful because in part D, we have the same variables. We kind of have the same exponents, but these are not like terms. One term has x squared. The other has y squared. So in this case, they are not the same because the terms do not carry the same exponents. And then in part E, this goes back to the directions above. It says all constants are like terms. Well, part E, both constants. So they must both be like terms. Even though one is negative and a decimal, they are both constants, therefore they are both like terms. At the bottom here, use vocabulary. Again, we must become very, very familiar with the terms that we are using today. Use vocabulary from this activity to describe a method that could be used to add polynomials without algebra tiles. Again, take a moment to pause and think about what this would mean. The final example of today is going to look at our second learning target, which is using properties of real numbers to add polynomials algebraically. Now, algebraically is just a fancy term for saying without manipulatives. Basically, on paper. Pretty much how we've been solving problems the entire year. And this is also going to go back to the beginning of the lesson when we separated out the like terms. So it's asking us to add these two polynomials horizontally and vertically. Now, for the sake of this lesson, typically we are going to use this horizontally, or this is the way I want you to use this. Very much so following these steps in line. First, identify like terms. I like how it uses the arrows here. 3x cubed is a like term to 4x cubed. Negative 5x has a like term with 2x. And then we have 7 paired with negative 3. The only thing I don't like is that it leaves the 2x squared out hanging by itself. So again, another method we could do is very similar to what we did in the first lesson, where I use different colors around the like terms. You could also maybe use different shapes. So I put a square around the cubes. I circled the squares. I'm going to underline the x values and maybe even put a triangle around the constants. That helps us see that there are more than just the like terms, but there are also other terms that are left by themselves. So from here, we group the like terms. This should sound familiar. We were just doing this with radical expressions. Group by like bases. Once we get to this point, guys, the last step is very important and it should seem pretty simple. The last step simply says add the coefficients. Just like your squares, we're adding the number of squares. We are not adding the coefficients. We're not adding the variables. We're simply increasing the number of that term. So we have 3 plus 4 to give us 7x. 2x squared is going to stay the same. Negative 5 plus 2 and 7 minus 3 gives us our final solution. Vertically is going to work for us, and it's going to work very well. Again, when I will do these problems in class, you will see me completing them horizontally. If you understand and like the method for vertical, you may do that. That is perfectly fine. However, in class, you will always see me following the steps for horizontally. So take a minute to look through this example before looking to the bottom of this page. The bottom of this page is going to be your final checkpoint with your sub. So I'm going to have you on your own work through A, B, and C. And then when you finish part C, you will have the sub check your answers. Once the sub checks your answers, you may begin to work on IXL on your computer silently. You may work on the homework that was or the IXL that has been assigned for the week, which is found on Homework Hotline, Or you may, again, look at Homework Hotline and look at the IXL that has been assigned for this lesson. But at this time, you are to complete A, B, and C on your own and have the sub check your answers. Before we end this video, I want to discuss number 7. It says, explain why the sum of two polynomials will always be a polynomial. Well, to think about that, we have to understand what is a polynomial. If we remember from the last lesson, a polynomial has more than 3 terms. So the answer for this could have a couple different answers. So we are not going to turn a polynomial into nothing. We could subtract everything away from it, and that's fine.